Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 8, 2025, about 2 days ago. The striking result is that adding artificial hippocampus networks cuts flops by 40.5% and shrinks the memory cache by 74.0%, while raising the LV-Eval average score from 4.41 to 5.88. The paper is titled, Artificial Hippocampus Networks for Efficient Long Context Modeling. And as we will see later, the efficiency gains come without sacrificing accuracy. In brief, this paper blends sliding window attention with a compact recurrent memory trained by self-distillation to rival full attention at long context. Also, the authors shared a GitHub repo. It includes core AHN implementations under SRC for RNN-style modules and transformer backbones, example and eval folders, and scripts to install, merge AHN weights into QN 2.5 models, run inference, and launch training. You will also find AHN checkpoints for Mamba 2, DeltaNet, and GatedDeltaNet. Alright, those code resources sounded practical for trying the models. Figure 1 presents the core idea and a headline result. Panel A depicts a sliding window that keeps lossless short-term memory, while an artificial hippocampus network compresses tokens that fall outside into a fixed long-term state, which then combines with the window output. Panel B reports the payoff. For QN 2.53b, flops drop by about 41%, memory cache shrinks by 74%, and LV-Eval rises from 4.41 to 5.88, with only a tiny parameter increase. Well, Figure 1 showed the headline gains. Figure 2 illustrates the workflow that delivers them, with a sliding window keeping recent tokens lossless, while a compact recurrent state stores evicted tokens so the query can read both sources. Panel A walks through a toy window of length 3 and shows the artificial hippocampus network updating memory as tokens leave. Panel B depicts the self-distillation setup, where a frozen full attention teacher guides training while only the artificial hippocampus network parameters learn. So the previous figure outlined training. Figure 3 compares efficiency and quality, and it highlights 4 aspects across sequence length. Panel A shows floating point operations growing roughly linearly with artificial hippocampus networks, while the baseline rises quadratically. Panel B shows the memory cache staying flat with artificial hippocampus networks, which matters because storage otherwise grows with tokens. Panel C reports stable low perplexity on the long PG19 book, even past the pre-trained context. Panel D shows lower peak GPU memory than the baseline across the same tokens. So, Figure 3 compared end-to-end efficiency. Table 1 summarizes where those gains come from, and it contrasts full attention with window attention plus artificial hippocampus network GDN. The middle column shows that full attention has compute that grows quadratically with sequence length, and a memory cache that grows linearly with length. The right column shows compute that scales with window times length, and a cache that stays proportional to the window, which keeps usage flat as sequences grow. Alright, the previous table explained the scaling rules. Table 2 presents head-to-head results and efficiency across LV-Eval and InfiniteBench, with consistent gains from artificial hippocampus network variants. Mixing compute drops to about 47 to 50% and total model compute to about 59 to 65%, while the memory cache falls to roughly 26%. On QN 2.53b, the LV-Eval average rises from 4.41 with full attention to 5.88 with artificial hippocampus network GDN, and InfiniteBench averages jump similarly at larger sizes. Okay, the previous table covered LV-Eval and InfiniteBench. Table 3 reports 6 long bench tasks with a fixed lossless memory of 8,192 tokens, so every method faces the same budget. Across QN 2.5 bases, artificial hippocampus network variants lead. At 3B, the DeltaNet averages about 35.9, at 7B, the DeltaNet reaches about 41.0, and at 14B, the GatedDeltaNet tops the group at about 41.9, while also scoring the highest trivia QA. Well, 2 takeaways stand out. Combining a sliding window with a compact recurrent memory delivers long context quality while slashing compute and cache, and self-distillation makes the module lightweight to add. The broader implication is practical long document reasoning on modest hardware with linear compute and flat memory. That is it for the AI Research Roundup. I am Alex, thanks for listening.